Good afternoon, Lahat. Our presentation today is about the next major version of TLS, TLS 1.3, which it has some good features, including zero RTT, which is is a new session resumption, but could lead to potential replay attacks. Our intent today is to give you, the audience, three key takeaways. First is to give you an understanding of this TLS 1.3 and also the new feature called zero RTT,
should be
zero round trip time resumption, and also is to give you and raise awareness across the audience about the security or potential security risks of this new feature, zero RTT. And the third thing that we want to raise with you is to give you recommendations about how you can mitigate those potential risks. So then a disclaimer here, what we are going to discuss here are just our own opinion and does not reflect the view of our employer. So let's introduce ourselves.
Hi everyone, my name is Alfonso García Alguacil. I work for Cisco as a senior security consultant. I mostly do penetration testing and research and development focused on offensive techniques. And of course, I'm glad to be here.
Hi, my name is Alejo Murillo Moya. I am a senior security consultant at Cisco. I am the red team lead for EMEA, Europe, Middle East, Africa, and Russia. I have more than 10 years of experience as a security consultant, and I have plenty of certifications, technical certifications. And as Alfonso said, we are really happy to be presenting here today. So now that we have introduced ourselves, let's introduce TLS 1.3. So first, a bit of history. So 4 years ago, a working group was created. And that working group had one mission. And that mission was to develop the new version of TLS, TLS 1.3. There has been 28 iterations on the protocol specification, also called drafts. And as you can imagine, it has been a long journey to go there, to the final draft. Let's move on and then see now which are some of the good things about the TLS 1.3 protocol. So one thing is that the TLS 1.3 has followed the keep it simple approach. And there is only 5 ciphers supported by the TLS specification. That means that if you are implementing the protocol, that's going to be much easier, and also that will reduce the complexity of the protocol. So imagine on previous version of TLS, we had dozens of ciphers. That's, if we compare that, now it's quite much better. We only need to support only 5. Also, another thing is that we, with TLS 1.3, is not going to be vulnerable to previous known attacks that has been on previous version of TLS. So you can imagine RC4 attacks, RSR attacks, CVC encryption mode attacks, or even compression attacks. Good luck finding them on TLS 1.3, because you're not going to find them. Another good thing is that TLS 1.3 supports perfect forward secrecy by default, and that's not like on previous version of TLS, which is something optional. Like here is it by default, and you cannot change it. And let me explain a bit more about the perfect forward secrecy. So imagine that an attacker is able to store all your secure communications. Perfect forward secrecy ensures that even if the attacker managed to get access to the server private keys, he wouldn't be able to decrypt your communications. And that's because ephemeral session keys are being used. And that's a good thing. Also about TLS 1.3, he went, I think, around like 2 different formal security analysis, where basically the TLS 1.3 protocol, its machine state, its security assumptions were analyzed, and some weaknesses were identified. And then what happened is with that information, the TLS protocol was refined and improved before its final release. Let's talk now about the compatibility issues. Last year, Chrome and Firefox were doing some field tests, and what they found is that around 5% of the users were having issues connecting to some websites using TLS 1.3. They investigated that, and they found that it seems that behavior was caused by something called middle boxes. A middle box is a corporate networking device which is inspecting or intercepting HTTPS traffic. So what happened at the end is that there were some modifications made to the protocol. Specifically, the TLS 1. Or the previous TLS 1.3 handshake was changed to look like a TLS 1.2 session resumption, and that fixed the issues with the middle boxes. So at the end, what we can say is that the protocol is not as pure as it could be. However, given the circumstances, I think that it was a good thing to do. And then let's discuss the focus or the topic for this presentation. So one of the things that the working group for TLS wanted to do is to have a faster TLS. And that's especially important on mobile networks due to latency. So ZeroRTT was born, and just a quick recap, ZeroRTT is a session resumption which push data to the server, or so-called early data. So basically, we will have two key sets of information. One is the session ticket, and the other thing will be the data, or the early data, which would be encrypted using a pre-shared key. Then when the server receives that message, it will verify the second session ticket, and then if he can decrypt early data, then he will start processing it. So with ZeroRTT, things are faster. However, it has some security implications. And which are those security implications? First is that we lose perfect forward secrecy on ZeroRTT messages. And second, the ZeroRTT messages could be potentially vulnerable to replay attacks. And that's something really important because we know TLS, we know it, and replay attacks was never one part of our concerns. But now with ZeroRTT, that's going to change because we need to take care of replay attacks. So why should I care, or why should you care? Hopefully, with the previous slide, I have convinced you. But if not, you need to, yes, and the protocol is not an internet standard yet. You just need to go for the formal release process, but your browsers are already supporting it. So Firefox, it supports TLS 1.3 and ZeroRTT by default. Chrome is already supporting TLS 1.3. What about the implementations? So we have OpenSSL, which the next version, which is 1.1.1, is on pre-release status and is going to support ZeroRTT and TLS 1.3. Boring SSL is the same. And you may have heard the news, but Facebook has just released their own TLS 1.3 implementation, which is also supporting ZeroRTT. And they said something interesting. If I recall correctly, I think that they said that around 50% of the traffic that they are seeing is using TLS 1.3. Also, the CDNs, if they are not supporting TLS 1.3, they will be planning to support it. So, in summary, TLS 1.3 is already with us, and its use is going to increase in the coming months or even weeks. So now, let's talk about the TLS 1.3 handshake. So imagine that the browser wants to speak with the web application using TLS 1.3. So it will send a client hello message, and he will make some educated guesses about which options or cryptographic options the server may choose. When the server receives that message, it will send back to the client the required cryptographic material in order to do the full handshake, and including the certificate and also a proof that he has the private key of the certificate. When the client will receive that message, it will verify that the certificate and also that proof he has the private key of the certificate is valid in order to ensure that he's talking with the right endpoint. And after that, the handshake has been completed. Once the handshake has been completed, application data can be transmitted securely. And as you can see here, there is something is called new session ticket that will be used in future communications. Now let's talk about the ZeroRTT session resumption. So imagine that you have a browser that needs to resume the session with the secure session with the web application. It will send a message to that, and it will have two key things. One is, as I mentioned before, the session ticket, and it will also contain the early data, or the data that it's going to be pushed to the server. Then the server is going to receive that message and is going to process it. basically, and it will verify that the session ticket is a valid one, and also that he can decrypt the data. And if he can decrypt the data, it will pass that information to the next layer, which will be the web application in this case. And then it will send back a message to the client saying that everything went fine. The client will receive that message, and then it will tell the web application that, okay, that's fine. We no longer need to send any more. I'm not going to send any more early data. Let's continue the secure communications. And as you can see, application data will be transmitted securely. So as you can see, it may be possible to do replay attacks. And that's because the only thing that an attacker needs to do is just to have a copy of that original message, which will have the right information. It will have the right session ticket, and it will have also a valid pre-share key. So let's see how an attacker may look like. So imagine that we have a banking application, and we have a customer that wants to do a money transfer or transfer of funds on that application. So when he clicks submit, the browser is going to send a 0TT message. So he sends a 0TT message, and in this instance, the attacker is not going to do anything, but he will keep a copy of that message. The server then will receive that message. It will verify that the session ticket is valid. It will verify the data that has been encrypted with a pre-share key, and it will unencrypt the data, decrypt the data, and push to the web application, which will perform a money transfer. So we have there the first money transfer. But what happens if the attacker replaces that original message? So as we can see here, the server will process because it's a valid message, and the web application will perform the second money transfer here. And as you can see, the attacker can perform as many money transfers as he wants because he just needs to send that message again and again. So is it everything as bad as it looks like? Not really. So the working group put a lot of effort in the TLS specification to describe all the security risks of using 0RTT, and also they put some protections and mitigations that can be used to mitigate those risks. So one of the protections that are mentioned on the RFC is single-use tickets. Single-use tickets is a protection against replay attacks that can be used by the server, which basically is he has a database with all the valid session tickets. In reality, what happens is that when the server sends a session ticket to the client, it adds it to his own database, and when he receives a 0RTT message, he looks up that session ticket with the database, and then if there is a match, he will remove from the database. If there is a replay attack, what will happen is that the server will look for that session ticket on the database, and he wouldn't find it, and then will say, okay, I'm going to reject that message because this is a replay attack. So this procedure seems to be really good. However, it has one issue, one challenge, and it's how you replicate that database across complex environments. And the database synchronization, that's the real key issue here. And because that will open a potential window for an attacker to do replay attacks. Another protection that is mentioned on the RFC is a client hello recording. In this instance, the server will keep a list of all the client hello messages that he's receiving. So if he's receiving the first 0RTT message, he will take the client hello and will store on his list. If there is a replay attack, he will receive the same client hello, and then he will look up at the list and say, oh, sorry, I have already received that message. So he will reject that message. So same as before, the challenge here is how you synchronize that list on complex, global, and distributed environment. The RFC also mentioned a mitigation which is called freshness checks. So when the browser sends the 0RTT message to the server, it includes a timestamp of when that data was sent, that message was sent. So what the server can do is he can verify that timestamp and reject any messages that are not within a specific time frame window. Applications profiles. The RFC, and let me see if I can let me see if I can quote it properly, says that application protocols must not use 0RTT data without a profile that defines its use, which basically means that the application should be able to define which functionality, which paths should be exposed over ZeroRTT. This application profiles is a related RFC and it's work in progress at the moment. And then we have other protections that can be implemented or mitigations. For example, OpenSSL has decided to segregate the normal TLS and the ZeroRTT API. And what they are trying to do is that if a developer wants to use ZeroRTT, that means because he really wants to do it and he knows that all the potential security implications of using ZeroRTT. Other protections that can be added will be added on the server or at the browser level. So for example, you can ensure that only ZeroRTT data is sent over HTTP safe methods, which would be get, head, or options methods. Also, another protection that can be done is to make sure that the application, the functionality of your application are replay safe and are idempotent, are only allowing idempotent actions. So idempotent actions basically means that it doesn't matter if you received the same request once or multiple times, the results on the database or in the backend is going to be the same. It's going to have the same state. And finally, the final protection could be just to disable ZeroRTT. So that will be the best protection. So let's see now a table that we have basically created, which what we have seen so far related to TLS 1.3. So the first two columns have the protections that are within the RFC, single-use tickets, and client hello recording. You don't need to implement both, you just need to implement one of those. The third column will be for the application profile, and then the fourth column will be for other interesting nodes. So for example, with OpenSSL, they have implemented single-use tickets, and as I mentioned before, they have segregated APIs for ZeroRTT and normal TLS. But in SSL, ZeroRTT is disabled by default. Then Cloudflare, they are working to implement single-use tickets. They have implemented application profiles using HTTP headers, and ZeroRTT is disabled by default. If you want to enable ZeroRTT, you need to do explicitly using the dashboard. And if you enable it, it will only allow ZeroRTT messages on safe methods, HTTP methods, which will be, for example, GET. And on top of that, they have added another protection, which is they are not allowing parameters on GET requests. With Chrome, ZeroRTT is not available yet. I think there are plans to work in progress in order to enable that. And with Firefox, ZeroRTT and TLS 1.3 are enabled by default. And it's only using ZeroRTT data on safe HTTP methods, which means GET requests can go over ZeroRTT, POST requests are not going to go through ZeroRTT messages.
Okay, we are going to show the impact of ZeroRTT when an attacker is in the middle of the communications path between the web browser and the web server. Of course, both the web browser and the web server will have TLS 1.3 and ZeroRTT enabled. As a web browser, we are going to use Firefox with HTTP2 enabled, which is already enabled by default. As a victim application, we are going to use our own banking application, which uses a GET request with REST format to perform a money transfer. Firefox only uses ZeroRTT for secure methods, but how many applications use GET to perform actions which should be made using POST or other methods? Well, we see a lot of them while we are performing web service assessments. In a normal situation in which there is not any attacker, the web browser will only send one request using ZeroRTT, the first one. Then the TLS connection would be established, and the rest of the requests will be sent using the created secure channel until the keep alive time times out. Therefore, it is highly unlikely that an attacker could catch a tempting request to be replayed only with passive techniques. But let's see this with a video. Okay, as I mentioned before, we are using the latest Firefox version. This is the tool that we created to test the replay attacks. It is in the middle of the communications from the web browser to the web server. And in this first mode, the only thing it does is show a message when 0 RTT is detected. The tool is not a HTTPS proxy, it is only a TCP proxy. And this means that the tool is not the TLS termination point, and therefore it cannot see the unencrypted data. However, it can see the TLS packet headers, and using it, it can detect when 0 RTT is used. This is our banking application. The domain points directly to the web server. And as you can see, the certificate is correctly validated, so the user will not notice that we are in the middle. As you can see, although we are performing some requests, nothing is shown by the tool because nothing is sent using 0 RTT. As shown in the timer, we go forward 3 minutes without perform any request to consume the keep alive time. Now that the keep alive time has been consumed, the first request that we perform will go using 0 RTT. Which is this one, and it could be potentially replayed. However, the next requests will be traveling through the established secure channel, and therefore they cannot be replayed. So this is why we think it is highly unlikely that an attacker can replay a tempting request only with passive techniques. Okay, but can we control when the web browser is using 0 RTT? So can we improve our attack? Okay, the response is that yes, we can. And I'm going to explain how. Here is the TLS full handshake that Alejo already explained. And after this full handshake, or even after a 0 RTT handshake, we want the server to receive the HTTP request and the web browser to receive the server response. If we don't do anything after this, the next requests, as you already saw, will be traveling using the secure channel. But we can finish the connection at the TCP layer using fins or reset packets, and then the web browser will send the next request using 0 RTT. If we do this for every new TLS connection, the most part of the requests will be sent using 0RTT, and therefore there will be much more chances to replay the request that the attacker wants. Let's see this with a video. And well, in this video, we are going to show also our first replay attack. This is the tool, same tool configured to do this last technique. Our banking application is now hosted behind Cloudflare with 0RTT enabled. Well, as you can see now, for the most part of the requests, are sent using 0RTT. Due to the use of HTTP2, some of the requests are not really sent using 0RTT because only the HTTP2 preface is sent over it, and the real request will be sent later. However, we have noticed that for the requests which are initiated using Ajax, for the most part of them, they are sent using 0RTT. Now perform money transfer, but this time we don't want to perform the replay, just to show that we are not tricking you. So we have only one money transfer. And now we perform a money transfer of $3. And we replay it 3 times. And refreshing the transactions list, we can see that the attack was successful. So the user only performed 1 money transfer, but we have 4 here. Coming back to the slides. Okay, so we have seen how a replay attack can work against a server or an application which is hosted behind a server which doesn't implement single-use ticket or client hello recording. But can we improve our attack? Is it possible to perform a replay attack against a server which is implementing this client hello recording or single-use ticket? The response is yes. In this situation, the web browser sends the HTTP request using 0RTT, and the attacker intercepts it. He sends the 0RTT packets to the web server, and the web server accepts it because it's a fresh 0RTT with a non-use session ticket. However, the attacker is not going to send back the server response. Instead of it, he creates a new TCP socket and sends again the same 0RTT packets. This time, the web server rejects the packets because it was using an unused session ticket. This time, the attacker sends back the rejection to the web browser. And according to the RFC, after a rejection of 0RTT, a full handshake has to be made. So it is made. And after this, the web browser will send again the same original request to the web server. And of course, the web server will accept it. But let's see this with another video. Oops, sorry. This is our tool, and in this case, it is configured to perform this last technique in combination with the killing technique to force the web browser to use zero RTT. The banking application is now hosted behind a reverse proxy with zero RTT enabled. It uses the pre-release version of OpenSSL, which implements single-use ticket. Like in the previous video, we perform a money transfer of $2, but we don't want to replay it. And as you can see, we have only one money transfer in the transactions list. However, now we perform the money transfer of $3 and we want to replay it. And refreshing the transactions list, we can see that the attack was successful again. The user only performed one money transfer, but we have two money transfers here.
Oops. Okay, let's talk about the side effects of zero RTT. So when we were deploying previous version of TLS, how the data was being transmitted was totally transparent to the web application. However, that's going to change with zero RTT because it adds a dependency between the TLS and the application layer, which has never happened before on TLS history. So that means that the application needs to be aware if zero RTT is implemented, because he will need to add additional protections to prevent replay attacks. So at the end, the ultimate defense will be on the application itself to make sure that replay attacks are not possible. So you could be asking how we can do that. So let's see the things that we can do to prevent that. So first of all, we can just disable zero RTT, and please don't enable it unless you are really, really sure what you are doing. All the things that we can do is just try to make sure that the application is not vulnerable to replay attacks, which one thing that we can do, for example, on the web application would be to apply a strict cross-site request forgery policy, which means that we are not going to apply cross-site request forgery at the session level or at the form level. It will be at the request level. Another mitigation that we can use would be to, for example, the GET requests that are not replay safe, they can be migrated to POST requests, mainly because the web browsers is likely that they are not going to send zero RTT data on POST requests. But that will depend on the browser implementation, though. Regarding the web services, if you are developing REST web services, make sure that you are following the good practices, and that means that you know how to use GET, POST, PUT, and DELETE properly. Regarding the GET the functionality that you are exposing over GET requests, please make sure that those actions are either just read-only or idempotent. And finally, please create a strict application profile which clearly defines which are the functionality or paths that are replay safe, so you are not exposing your application to zero RTT, to functionality that is not replay safe.
To finish this presentation, we have here 3 takeaways. The first one is that TLS 1.3 is awesome, and all of us should use it, but take care if you use zero RTT or you enable it. The second one is that your application should be zero RTT aware to prevent side effects. And the last one is that maybe you need to change your application or your server configuration in order to avoid replay attacks. Thank you so much. And if you have any questions,